as the assignment problems. Okay. Now, as the name itself says, when we say assignment problems, that means we are going to handle problems in which we have to assign something. Okay. Now, in the sense that we may have some jobs that need to be done by some workers. Okay. But the condition is that one job can be assigned to only one worker. Or in other words, one worker cannot be given more than one job. Okay. So then not only this, now there is a cost involved because we have to pay to the worker for any job that he or she is doing. Okay. So that means, again, the cost is involved, right? So the objective here is to assign these jobs to workers. That means, say, supposing I have, say, 5 jobs, A, B, C, D, and E, and I have 5 workers, 1, 2, 3, 4, and 5. And the situation is such that each of the worker can do each of the job. That means my worker 1 can do any of these 5 jobs that need to be assigned. Similarly, worker 2 can do any of the 5 jobs that we need to assign. So the workers can, each of the worker can do any of the job that needs to be assigned. But then there is a difference in the cost. That means worker 1 will charge some amount to perform task A or task B and so on and so forth. Okay. So when we say the objective here is to assign these jobs, I mean, which job should be assigned to which worker so that the cost of getting the job completed is minimized. Okay. So that means the objective here is a minimization problem, because we are minimizing the cost. I mean, it's not that we cannot maximize the things, we can, but the way to handle maximization problems in assignment is slightly different. Okay, so that means we'll for the time being be handling only the minimization problems, right? Now, the thing is that these assignment problems, see, we have seen transportation problems. Okay. Now, in the case of transportation problems, we had what? We had sources, we had destinations. Okay. Now, supposing instead of sources, I take workers. Okay. And instead of destination, I take the jobs that need to be performed. Okay. So it's more or less the matrix is similar to that of transportation. But the only difference is that in case of transportation problem, we had additional information on supplies and demands, you know, how much a particular source can supply or how much a particular destination has a demand. Okay, so depending upon their supply and the demand, we had constructed a transportation problem. But now the thing is that, like, say, supposing I have, say, 5 workers. So in a way, I have 5 rows and I have 5 columns. Okay. Now, since one worker can be assigned only one job, that means the total supply, you know, if I compare this with the supplies, it has to be 1 because it cannot be more than 1. Similarly, since one job cannot be given to more than one worker, so that means even the total demands to be met is only 1. That means one job, one worker can do only one job, and one job can be done by only one worker. So this is the only difference here. That means the sum total of each row and I mean, it's not the sum total now. It's just that the entries in each row and entries in each column is 1. Okay. And since we need a balanced transportation problem, so that means my number of rows must be equal to the number of columns. Okay, my jobs to be assigned must be equal to the number of workers who can perform that job. Okay, that is the only additional requirement. So what happens is that in this particular case, a typical assignment problem or a typical assignment table, now it looks like this thing only. That means what we do here is we talk of resources here, which are nothing but the workers. Okay. who will be performing the jobs, and then we have the activities to be performed. Okay, which are the jobs, right? So it's like, say, supposing you have W1, W2, and so on, say n number of workers with you, and accordingly you have, these are the jobs, J1, J2, Jn, the n number of jobs that you have. Okay, so this is how the things are going to look like. But instead of supplies and demands, now we'll have one worker. One can do only one job. Worker two can do only one job. Worker n can do only one job. Okay. Similarly, the first job has to be completed only by one worker. So first job has to be completed. Second job has to be completed. And similarly, nth job has to be completed by only one worker. Okay. Now the costs here, like if I say C11, C12, and C1n, similarly C21, C22, C2n, and CN1, CN2, CNN. So basically Cij here denotes the cost involved. Cij here is the cost if the ith worker is assigned the jth job. Okay, so if worker 1 is assigned J1, then this will be the cost involved. Similarly, worker 1 is assigned job 2, then this will be the cost, and so on and so forth. Okay, so and the variables that we define here, now this is slightly different. In case of transportation problem, our decision variables were Xijs, right? Now Xijs were what? Xijs were the number of allocations from the ith source to the jth destination. Okay, now since I just have to assign jobs, that means Xij will take on a value only if the ith worker is assigned the jth job. Otherwise, it won't take on any value, because either a worker is being given a job or a worker is being not given a job. There is no other option available here. Okay, so we say Xij takes on the value 1 if the ith worker is assigned the jth job. Otherwise there is no assignment. So that's why, see, that's why we are calling it as the assignment problems, because we are assigning the jobs here. Okay, and Xij takes on the value 0 otherwise. Okay, so these are the only options. So that means, I mean, you see, in the earlier case, in the transportation problem, Xij was also a number, because we had fixed supplies and we had fixed demands. Those supplies had to be distributed. But now in this case, it is only one. That means my variable, see, these are the values only which my variable can take. There is no other option. So Xij can be either 1 or Xij can be 0. There is no other option possible. So basically that means this Cij, see, otherwise the objective function becomes what? Summation of Cij, Xij. And not just this, this is always a double summation, as we had in the case of transportation problem. So it was I also runs from 1 to n now, and j also runs from 1 to n. So this is your z, which is to be minimized. See, mind you, Xij is taking the value either 1 or 0. So if it's taking the value 0, that means these costs are not contributing to the objective function. So the contribution of these costs is coming from only those cells where an assignment is being made. In the sense that, say, supposing if the second worker is assigned first job, so that means it's C21 which is contributing to the objective function, nothing else. No other, no other I2, I equal to 2 is making any contribution, because we can assign only one job to one worker, not more than that. Okay, so that's how the objective function is going to be defined, and this we are going to minimize. But then this, in fact, the constraints, they remain same as we had in the case of transportation problem, because we had the constraints based on resource availabilities and the constraints based on demand destinations. So we had summation xij is equal to a1, a2, a1, and so on and so forth. But in this case, the right hand side is all one. So that means the only concept of constraints that we are going to have is this only, where once we are running over j and once we are running over I. So these will be your set of constraints. So one is based on the resource availability or the worker availability. These are the resource constraints, and these will be based on the activity requirements. What are the requirements of a job? Okay, that's it. And there is no non-negativity restriction because my xij is either taking a value 0 or 1. So this is what a typical assignment problem looks like, where you have to minimize some cost attached to it subject to these set of constraints. Okay. Now, again, it is a linear programming problem because your objective function is linear, your constraints are linear, you have so many n plus n, 2n number of variables in your problem. But it's just that out of those 2n, only a few can take on the value 1. The others will take on the value 0. Okay. So the point is that, okay, I mean, though it is a linear programming problem, we have various methods to solve this linear programming problem. I mean, of course, we won't be discussing all, we'll be discussing only one, but there do exist so many methods of solving an assignment problem. The very first is your enumeration method, okay, where we directly enumerate how the assignments should be made, okay. Similarly, we have the simplex method. That means we solve, because see, mind you, again, these are equality constraints. So to solve it by using a simplex method, that means we have to introduce so many artificial variables and then solve by using the simplex method. So that is the direct method of using simplex here. Okay. Then we have transportation method. That means the way we solve a transportation problem in a similar manner, we solve this assignment problem. That means we start with initial basic feasible solution. We check for optimality. If it is optimal, we terminate. Otherwise, we move on. Okay. The way we solve a transportation method by using Modi method and so on and so forth. The last method, the one that we would be doing typically for solving an assignment problem is what is known as the Hungarian method. Okay, this is what we are doing. So this is basically, Hungarian method is again nothing but an algorithm that has been developed to solve assignment problems alone. Okay. Now, Hungarian method, we call it as Hungarian method because it was given by a Hungarian mathematician by the name of D. Koenig. He gave this method to solve assignment problems. So that's why it's called as the Hungarian method. Okay. Now, again, since it's an algorithm, so definitely it has to start with something, it has to end with something. And the best part is that this algorithm terminates when an optimal solution is reached. So optimal solution is reached means, there is no further reduction in the cost possible. Okay. So again, since it is in fact algorithm, so it has its steps involved in it. So we'll be doing those steps one by one. Okay. Now, in fact, the kind of table that I gave above, that is called as the opportunity cost table, okay, or the opportunity cost matrix. Okay. So the very first step, while we are following the Hungarian method, is to develop the cost table for the given problem. Okay. If it's the table given, fine. Otherwise, from the given information which you have in your problem, we develop the cost table. Now, again, in this case, we have to keep in mind that your number of rows must be equal to the number of columns. Okay. Now, because then only it will be a balanced problem. Huh? In case they are not equal, that means in case the number of rows is bigger than number of columns, or in case number of columns is more than number of rows, then as in the case of transportation problems, we introduce dummy rows or columns. Is that clear? Hmm? So depending upon, depending upon the requirement, whether we want to add a row or we want to add a column, we introduce dummy rows, and the costs in the dummy rows or columns are always taken as 0. Is this clear or not? Hmm?
Yes, ma'am.
Okay, fine. So we move on. So first step is okay. That means just like in the transportation, the very first thing we check is whether it is balanced or not. In a similar manner, we are checking whether the number of rows is equal to the number of columns or not. Okay. Then in step number 2, we form the opportunity cost table, in the sense that what we do is, now see, this has to be understood and listened to carefully. What we do is we locate the smallest element in each row separately. Okay, so each row is to be handled separately. Locate the smallest element in each row and then subtract that from each element of that row. Okay, not the table, not the matrix, just the row. Okay, so from each row, we would pick up the smallest element and we would subtract that element from each element of that row. Okay, once this is done for all the rows, then that becomes a reduced matrix. That means we had some initial matrix with us in which we had performed some operations on rows. So what happens? That becomes a reduced matrix. Okay. Now in the reduced matrix, what you have obtained from above step, I'm calling that as the reduced matrix. So in the reduced matrix, we locate the smallest element in each column now. Okay. We have to begin with rows. So mind you have to remember that. Okay. So in the reduced matrix, we locate the smallest element in each column and subtract that from each element of that column. Okay. So now see, when you subtract smallest element from each row, so that means you have subtracted that element from the smallest element also. ठीक है ना? So that means कहीं ना कहीं तो zero आएगा ही आएगा. Now when you repeat the procedure for the columns as well, so what will happen is that each row and column, okay, will now have at least one zero. Right? हो सकता है एक से ज्यादा भी हो, that is a different issue, but at least one zero would be there in each row and in each column. Okay. Now comes the third step, which is crucial because now we are going to make assignments, and these zeros that we have got, they are going to help us assign things. Okay. So step number 3 here would be to make assignments as follows. I mean, how do we go about making assignments? It will be as per the following steps. So first row is, what we do is we examine rows successively, I mean, one after the other, we keep on examining until a row with exactly 1 0. I mean, this could happen in the first row itself. Fine, no problems. But in case it doesn't happen in the first row, we go to the second row, we go to the third row, and so on and so forth. Till what happens? Till we get a row with exactly 1 0. And this 0 I'm writing unmarked. I mean, we have not marked the zeros as well. The moment we do the markings, it would be like assigning. Okay. So until 1 0, unmarked 0 is obtained. Okay. Now what we do is we make an assignment. I mean, wherever only 1 0. See, this amounts to saying if I have a row with exactly 1 0, that means for that particular worker, there is only one option where job can be assigned. I mean, in whichever column that 0 is occurring, that becomes the job. That means there is no other option possible. So what we do is we make an assignment, right? And we mark that 0 with a square. Okay, around that 0. Now, is this clear? Bolo? Okay. Now, once we have made, I mean, see what has happened. That row had only 1 0, right? We don't know the remaining zeros in that column, right? Now, once we make a square around that 0, that means we have assigned that job to a particular worker. Okay, so that means that job cannot be assigned to any other worker, right? So what we do as a next step is that for each, I mean, and this can, the way we are doing markings by marking a square, this can be done for more than one row in a particular go. Okay, so for each 0 value that becomes assigned, that's what we write. So for each 0 value that gets assigned, we strike off all other zeros in that column. We strike off all other zeros in the entire, I mean, just write this row or column. Okay. Now, then what we do is once we have striked off, then we again revisit. Okay. So basically, we repeat steps A and B for each column now. Okay. That means now we will look for each column that has only 1 0 that is unmarked. Okay. We mark that and then strike off all other zeros in that row and so on and so forth. Okay. Now now what are the situations you can end up with? One is that okay, there's no confusion, nothing, and you are you are repeating these steps and you get your solution. The other could be that if a particular row or column has 2 or more unmarked zeros, you may end up with this. Okay. Then we assign arbitrarily, that means it's random, the choice is totally random. Then we choose the assigned 0 arbitrarily. Okay, that means I'll do a problem right now and then maybe this would be arbitrary. Okay, and when do we terminate? we continue this process until all zeros in rows or columns are either marked or striped off. Okay, we continue this process until all zeros in rows or columns, see, remember, mind this step is important, in or columns are either marked, marked means they are marked with a square, or striped off. That means there should not be any zero in the table that has not been either marked or striped off. Okay, like for example, see, let's start with, then we'll move to the next step, which is your actually your optimality criteria. Say for example, now I'm doing a problem which probably is very simple in the sense that, say, supposing I have, as I was saying, I have 5 workers and 5 jobs, okay, that need to be completed, and the cost involved in completing these jobs is 29271. Then then it is 68761, then 46531, then 42731, and 53951. Okay, now this is the assignment problem. We have to assign 5 jobs to 5 workers so that the cost of completing a job is minimum. Okay, this is what we have to do, right? So we have, now the very first thing that we were to check was number of rows is equal to the number of columns. So there is no need to add a dummy row or a dummy column, right? So we move to the next step. So what is the next step? We find the smallest element in each row, right? In the first row, what is the smallest element? 1. So we have to subtract 1 from each of the first element of the first row. Okay, so that means, as a, see, this is going to happen in these problems. You will have to make these tables as many times as you are performing the operations. Okay, so we have 1, 2, 3, 4, and 5. Okay. So we begin by from the first row, and we subtract 1 from each element of the first row. So it becomes what? 2 minus 1, 1, 9 minus 1, 8, 2 minus 1, 1, 7 minus 1, 6, 1 minus 1, 0. Now in the second row also the smallest element is 1. So we subtract that from each element of that row, and we get 6 minus 1, 5, 8 minus 1, 7, 7 minus 1, 6, 6 minus 1, 5, and 1 minus 1, 0. Similarly, in the third row also the smallest is 1. So it becomes 3, 5, 4, 2, 0. And the fourth row, I hope you are doing it along with me. So it becomes 3, 1, 6, 2, 0, and 4, 2, 8, 4, 0. Okay, now see, mind you, we have only performed this operation on rows. What was the next thing? To look for the smallest element in each column and subtract that, right? So we are going to get another table now, in which again I have 5 workers and 5 jobs, and my opportunity cost table is now going to be something like, now we look at the columns, right? Now columns kahan pe? In the reduced matrix that we have obtained. Now in the first column, the smallest element is 1. So we subtract 1 from each element of that column, and we are going to get 1 minus 1, 0, 5 minus 1, 4, 3 minus 1, 2, 3 minus 1, 2, 4 minus 1, 3. right? Similarly, in the second column now, again, the smallest element is 1, right? So we subtract all the elements. So 8 minus 1, 7, 7 minus 1, 6, 5 minus 1, 4, 1 minus 1, 0, and 2 minus 1, 1. And the third column, again, the smallest element is 0. So it becomes 0, 5, 3, sorry, just a minute, just a minute. I didn't see while writing. So it's 0, 5, 3, 5, 7, right? Now in the fourth column, the smallest element is 2, right? So we subtract 2 from each element of that column. So it becomes 4, 3. Now there are two 2's together, so they become 0, 0, and 4 minus 2, 2. Now the last column is all 0. So even if you subtract, the smallest is 0, you subtract 0 from 0 and you get 0, right? Now this is your final reduced opportunity cost matrix. Okay. Now what is to be done? We randomly look for rows that have exactly 1 0. Now the first row has 3 zeros, so we move to the second row. My second row has exactly 1 0. So what I do is I mark this 0 with a square, right? But the moment I have done this, I have to strike off all other zeros in that column because the fifth job is already assigned to the second worker. So fifth job cannot go to anyone else. So we strike off those zeros, right? Then what we do, we move to the third row. Now third row has only 1 0 left now. Okay. So what I'm going to do is mark it with a square and look for whether there is any other 0 present in that column. Since there is, I strike off that, right? Now I move to the fourth row. There is only 1 0 left. I mark it. Okay. Now there is no other 0 in that column. Okay. So, and there is no 0 in the fifth column, mind you. Okay. Doesn't matter. Now we repeat this procedure for each column. Now, if I look at the first column, there is only 1 0. So I mark it with a square and in that row, I strike off the 0 which was present. Okay. Now I see. Is there any 0 left that has either not been marked with a square or not striked off? No, everything has been marked. Okay. Now, before we move on, just let me know, is this procedure clear to all? Because this is important.
Yes, ma'am.
Okay, na? So this is how we are moving on. Now, we have to now check whether we have reached optimality or not. So that becomes your step number 4. Okay, we have just performed 3 steps till now. So your step number 4 is basically your optimality criteria. Okay, so I'm writing that as step 4, which is your optimality criteria. Okay. Now, in this case, what we'll do is we'll count the assignments that we have made. Okay. And we say that if the number of assigned cells, see, the zeros that you have marked with a square are actually your assigned cells. Okay. So this amounts to saying that I have assigned the worker A with the first job. Okay. So they are the assigned cells. So if the number of assigned cells is equal to the number of rows or columns, so this is what we want. Each worker should get a job and no job should be left unassigned, right? So that means, and since we have equal number of rows and columns here, that means each cell, the number of assignments must be equal to the number of rows or columns. Okay, so if they are equal, then it is an optimal solution. Okay, so that means what do we want? We want our number of assignments to be equal to the number of rows or columns in the opportunity cost matrix. Okay, so if the number of assigned cells is equal to the number of rows or columns, then it is an optimal solution. Okay, and in this case, your total cost which you compute will be equal to the sum of the original cost values in the occupied cells. That means we just compute how much was the cost when, say, supposing the worker A is assigned the first job. Similarly, whatever assignments we have made, and so on and so forth. Okay. Now, if we just look at our problem, how many assignments have we made? We have made only 1, 2, 3, and 4. So we have made only 4 assignments. That means, see, if you just look at this, your worker 5 has not been assigned any job, and job 3 has not been assigned to any worker. Okay, so that means definitely it is not an optimal solution, because my number of rows is 5, my number of columns is 5, and the number of assignments that we have made is 4. So they are not equal. Okay, so that means it is not an optimal solution. That means what? That means that your solution can be improved further. Okay, so it is like your initial solution that you have obtained. Okay, but it is not optimal. It can be improved further, right? So that is your next step. So if it is not an optimal solution, then we move to the next step, which is your 5. Okay, so if not optimal, then move to step 5, which is an improvement over the existing solution. Now, in step 5, what we are going to do is we are going to revise the opportunity cost. Okay, now see, the logic in all the problems is the same, right? In the sense that obviously, if it is not an optimal solution, that means the assignments that we have made are not right, right? So that means somehow from the remaining elements, some has to become 0, and one marked 0 has to become non-zero. Okay, so that assignment will not be considered and some other new assignment needs to be made. So basically, this is the job. Again, similar to one basic variable becoming a non-basic variable and one non-basic variable becoming a basic variable. Okay. Now, since it's going to take time and it's almost your class time, so I'm the revision method. I mean, how to revise the opportunity cost matrix. I'll do it in the next class then. Okay. So I'm winding up right now.